Okay, so these are our rules for fractional exponents. Kind of the important ones are the denominator is what becomes your index. If you have a numerator, that's an exponent, a normal exponent. So the numerator is an exponent and the denominator is your index. So if we look at this example down here, we can write it a couple of different ways. Remember, our numerator is a power, so we could write this as 4 to the third, and our denominator is the index. So we can do a square root. You don't have to put the 2 there. I'm just doing it so that we can see where the 2 went. That is 100% a valid way to write it. That doesn't help us simplify super much, unless you happen to know 4 cubed off the top of your head and what its square root is. So we can write it another way, and we can do the square root of 4 to the third. These two things both mean this. These are identical. But this one's might be a little bit easier to simplify. Because what is the square root of 4? 2. What's 2 cubed? 8. It's not always going to be that this way is easier to simplify. Sometimes this is actually easier. So to be able to write it in both directions is handy. And we're going to practice that a little bit. But your numerator is an exponent that's normal. Your index is the denominator. Okay. We're going to practice it a few times. It starts out simple and it gets harder. The ones like this are more like the, these are the kind that are like on the homework. But we're going to start simple. So we have our numerator of 1 and our index of 2, which means this becomes the square root of 9 to the first, if all we do is switch around our index. The square root of 9 to the first we can write as square root of 9, which is 3. Ooh, I know that one was a hard one. Sorry, I sarcasm a lot. So then on the 27, again, we have a numerator of 2. This time we have a denominator of 3. So we take our 27, and we're going to take the cube root of 27 squared. Yeah, and sometimes it's just easier to do it this way. Because, yeah, the cube root of 27 is 3. 3 cubed is 27. So this leaves us with 3 squared, also known as 9. Okay? How are we feeling here? Okay. Because now we're going to get into some more weird looking ones where we're going to have to use some of our other exponent laws that we were doing yesterday, and we need to simplify this before we deal with any of those roots. Don't toss them straight into roots, go into simplifying first. So I have 2 things in parentheses. They're being multiplied together. If it helps, put your numbers and your letters together in a way that makes sense to you. Because you could rewrite this as -5 times 2 times a to the 3/2. Oh, so that's bad. Times a to the 1/2. If it helps you to rewrite it with your numbers together and your letters together, that's valid. You don't have to, but you can. But it makes it easy to see what's going on. We have -5 times 2, which gives us negative 10. That's the easy one. And when we multiply our bases, that's an A. It looks like a 9, but it's an A. I'm just bad at writing. When we multiply our bases, what do we do with our exponents? Add them. So we have 3 halves plus 1 half. We get A to the what? 4 halves. Can we simplify 4 halves? What is it? Negative 10A squared. So sometimes you won't even have to mess with the indexes and it'll simplify. When you're looking at showing work, you do not have to hit all of these steps. Follow your brain's path. You do not have to write out as many steps as I do. Okay? Questions on these 3? Okie dokie. Because now we have to do a little something else. We are going to be rationalizing denominators. What that means is, this is probably new because we don't typically do this in other classes. Technically, leaving a radical in a denominator is bad math grammar. It's not wrong, but you will never see it in an answer key. We don't like radicals in the denominator because mathematicians be extra. It's really the only rule I have for that is it's because mathematicians don't like it, so they made more rules because, ugh. But whatever. So what we do is we multiply it by 1. It's just going to be a weird looking one to make the bottom be a whole number. So there's this little table here to try and help you see it. It doesn't help me, but I gave it to you. What we're going to do is we're going to look at this and say, all right, I've got the square root of 5. I'm going to multiply this by something that'll make that be square rootable. Which sentence didn't make sense either. But if I multiply the square root of 5 times the square root of 5, I can make that be square root of 25, right? 5 times 5 is 25. But I can't just willy-nilly multiply by square root of 5 even though it makes it do what I want it to. I can multiply by a very strange looking 1. Because that's 1, right? Square root of 5 over square root of 5, that is 1. Weird looking 1, but it's 1. The reason we want to do this is if I multiply across, because we're multiplying fractions, 1 times square root of 5 gives us square root of 5. Square root of 5 times square root of 5 gives us 5. And I no longer have a radical in my denominator. That is the goal, to get rid of the radical in the denominator. It means the same dang thing. You type it in a calculator, 1 over square root of 5 is the exact same thing of square root of 5 over 5. Means the same dang thing. It's just math grammar. Okay? So we're going to be multiplying by whatever makes our denominator not have a radical anymore. Okay? It's called rationalizing. It's a little weirder when we have cubes, like I have 1 over the cube root of x here, because we have to figure out how many more x's we need to make that be cube rootable. And what it is if I just multiply by square root of x, I'm not going to have enough x's. So we have to do the cube root means I need a grand total of 3 x's. I only have 1, so I need 2 more x's. Cube root of x squared. Cube root of x squared. It's really weird looking and it feels really weird. And it's going to feel really weird for a while. And that's normal, okay? So if it's feeling weird and it feels wrong, you're right. It feels weird and it feels wrong. Okay? So don't freak out if it feels wrong. Because if we multiply across, When I take the cube root of x times the cube root of x squared, remember in radicals we can multiply what's underneath. So we get the cube root of x squared on top and the cube root of x cubed. See what's happening? Kind of. Remember when it's in the radical, if they have the same index, I can multiply the pieces underneath, right? So I've multiplied my x times my x squared and combined it here. Since I have my cube root of a cube, we get cube root of x squared over x. Because the cube root and the cube cancel out. Yes, Em?
You get 3 by adding x or no?
So we multiplied x times x squared to get our x cubed. Okay? Because these two pieces multiplied together. And this is just our really crazy looking one. Okay? Rationalizing the denominator is the most obnoxious thing, just saying. When I saw we had to do that, I was like, ugh. I like a lot of math things. Rationalizing denominators is not one of them. Ugh. But we're going to do it anyway. Okay, so we're going to use some of our radical rules, combining some things together, because now we have square root of 2/3, and we are asked to rationalize it. Right now, it doesn't look like it needs rationalizing until we remember when we can take our root and a fraction and split them into two pieces. I'm going to zoom it in on this one just so we can see it better. Because to simplify this, we take our square root of 2 over the square root of 3, right? They mean the same dang thing. I changed nothing from here to here. Ooh, that purple really blends in with the black. I changed nothing from here to here. In order to get the root out of the denominator, I have to multiply it by a funny looking 1. What are we going to put in our denominator to make that not have a radical anymore? Square root of 3. When we have square roots, it's really easy because it should be the same exact thing to make it a perfect square. Okay? So now we have two fractions that we're multiplying. And we can combine them into one big radical. If it helps you to do this step, you can. 2 times 3. 3 times 3. I'm just doing this so you can see it. You do not have to write this step out, just because since we had a couple people get lost on that step, I'm drawing one more step in so we can see it, okay? This is doing the multiplication. It's going to give us the square root of 6 over square root of 9, which is 3. So we have the square root of 6 over 3. And I'm getting out of the way. And that, what is that? That is our answer. Love when my pen decides halfway through a shape to stop drawing. Okay? When you're showing work on stuff, that you do not have to do that many steps. Hit 1 or 2 of them. Okay? You do not have to write out as many steps as me. I will always probably write more steps than you. Are we okay on that one, on how that's working? Okay. Because it gets a little weirder. Because now we have a 5th root, index of 5. Okay, so these are I'm going to zoom it in so we can see. All right. So we're going to do the same kind of thing we did on the 2/3. We're going to split it into its fraction. I'm going to take our 5th root of our numerator and our 5th root of our denominator. And that's our fraction bar, just so we can actually see that. And then we have to figure out what our funky looking 1 is going to be. We know it's going to be a 5th root because it doesn't work if the index is not the same. How many more y's do we need? We need 3 more y's. in order to make it fifth rootable. And whatever I have on the bottom is what we put on the top, y cubed. It's fine. Code red's the best.
Yes, it is. Thank you.
Best.
Everyone was arguing.
No. Without debate. Without debate, code red's the best.
Absolutely.
I just had to get off of the Mountain Dew because it was killing my teeth. So I drink coffee now. This literally gets filled to the top every morning.
Is that better for your teeth?
Less acid. There is actually significantly less acid in coffee than in soda because of the carbonic acid used to make the carbonation. My dentist was getting grumpy with me. So, okay. Anyway, sorry, distraction. If y'all can't tell, I'm ADD. Shock, right? Oh my gosh. Y'all have known me a week. Okay, so our numerator is going to be that fifth root. We have our x times our other one times y cubed. What are we going to have in our denominator? Just y. These two pieces mean the exact same thing. For some reason, mathematicians like this one better. I don't know why, but they do. I don't get it. I think that one's simpler. This is the one they like better. It's the thing. We have to do it because that's what they, the imperial they, say we have to do. I don't get it, but we know what we're told. That's our answer, okay? I don't get why we don't have rationals in the denominator. Did never work for my brain, but that's me. Okay, couple more. They get a little crazier. These are our last two, and then we'll have time to work on the homework just a little bit and ask some questions maybe. Okay, so it uses some of those exponent rules. We're starting to work some of those things in. Okay, so we've got a square root here. But I'm going to split it up. Remember, this negative exponent takes this guy into a denominator. So what we have now is the square root of 9y to the 6th over x to the 4th. The negative exponent only moves that one piece. Then we're going to use our radical rules. We've got the square root of 9y to the 6th over the square root of x to the 4th. Do I need to multiply by anything to rationalize this? No. Square root of x to the 4th is x squared. So we can just simplify this. Sometimes the book tries to trick you, make you do more work than you need to, because they're not very nice. Okay, so what's our numerator going to be? 3y to the 3rd. This one rationalizes itself just by simplifying. Because we have 6 y's here, and square roots means we pull out pairs. I can make 3 pairs of y's. I always think of radicals like socks. Square roots means we need pairs of 3 or pairs of 2. If we had an index of 3, I'd need groups of 3. Index of 8 means we've got an octopus wearing socks. So we need 8 out of the octopus. Because that's the way my brain works, y'all. My brain's weird.
What has odd numbered things?
An injured ant.
Okay, that's sad.
So you could have, for like a 5, you could have an ant that had one leg stepped on.
That's sad.
It's sad, but he still deserves socks.
He does.
I think squids have 7.
Oh, squids can be between 6 and 10, I think.
So squids work for whenever we have anything odd and high. So just saying, that's how my brain works. Is radicals or socks?
That's interesting.
Because you need pairs. So sorry, welcome to my brain. Okay, so now we're going to do this 4th root one, and this one has lots of pieces. So first thing we're going to do is we are going to take our fourth root and we're going to split it to our numerator and our denominator. 5x to the 8th y cubed over our fourth root of 27x squared. There is a hard way and an easy way to get the 27 to rationalize on a fourth root. If you rewrite it as something with an exponent, you're probably going to save yourself some work. So how can I rewrite 27 as something with an exponent? 3 to the third, right? So if we do, I'm going to rewrite this whole thing, but if you just erase your 27, you'll see the same point. A third over fourth root of 3 to the third x squared. Now when we're looking to make our fourth root, and I can, there we go, just to give us some more space so I can make that not be on the bottom of the screen. When we're looking for our funky looking one to rationalize here, what pieces do we need? We need a 3 and 2 x's. We need x squared. Does everyone see where those pieces come from? Does anyone not see where those pieces come from? Okay, so by switching the 27 to be 3 cubed, because 27 is 3 cubed, we can see that I only need one more 3 to get up to 4. Because when it's 4, we're getting socks for cats. We need 4 socks. We need a group of 4 to be able to pull out for that radical. So by making an additional 3, that's going to get this up to 3 to the 4th. 2 more x's gets this up to x to the 4th. So when we're writing our next one, after we multiply across and combine our 2 pieces together, we're going to have our fourth root, this is our numerator, of 5x to the 8th y cubed times 3x squared. I'm just smushing them together right now. And then we have our fourth root. We have our 3 cubed times x squared times 3 times x squared. I just smushed them together. I didn't simplify at all. Does everyone see how that worked? Because this one's kind of our most obnoxious one of the day. I see us stretching in the back. I will scooch it up, and I'm trying to make sure we still get that top line. There we go. Feeling okay on that one? Because we got more to do. We got to simplify this. Fourth root. What's our numerator going to be? 15. X to the 10th. Y to the 3rd. And our denominator is going to be 3x. We have one more simplification we can do. Look at our numerator. Not the 15 and 3. Can I pull a group of 4 out of something? Out of the x's. How many groups of 4 can I take out of x to the 10th? 2. So we can have x squared, fourth root. How many x's are left over? 2. X squared y cubed over 3x. That is our fully rationalized answer. And holy cow, did it take a lot of space. I will zoom it back in so you can see the answer part, and then I will zoom it back out to see the sarcasm of that it is. Okay, so rationalizing a denominator is all about getting rid of all the radicals. Yes, sir. Yeah, I will zoom it all the way out so we can see it. I will also post a PDF of this on the Canvas page. I will always try, I'm not perfect, but I will try to record every day and post a PDF every day of our notes. At the very least, I will get the PDF because my computer saves that. If I forget to hit screen record, I try. Okay, so I will always post it. I do have the videos posted for the last 2 days of notes we've taken. Got the PDFs of those notes up already. Okay? So this is one of the more complicated ones, like on the homework. This one actually is straight up pulled out of a question next to one on the homework. Homework is page 26 in your book. It is also online. I have a digital copy up. I also have 3 extra copies of the book in the back in case you don't want to carry the beast around, because it is a beast. But this one, yeah, this one was 71, and one of the homework questions, 70, is very, very, very much like it. And 74 is also very, very, very much like it. So this one was question 71, which is not a homework question, but it's right next to 2 of them. Okay? So, those are the question numbers for homework 1, 2. It's due Wednesday, tomorrow. Tomorrow is also when we have those course meetings. Okay? While you guys are working on that, we have about 15 minutes for you to work on this. I'm going to pass back homework 1. The grades for that are already in.